Welcome to the BrainOmega channel. In today's session, we're diving into a crucial topic in the world of artificial intelligence. The main goal of this tutorial is to take a significant step forward toward understanding and implementing LLM alignment within our community. So, what exactly do we mean when we talk about alignment in large language models? At its core, alignment isn't just about making an AI smarter, it's about making it wiser and more responsible. As you can see on the slide, alignment is the dedicated process of training and fine-tuning an LLM so that its actions and responses are consistently in sync with human values and intentions. The ultimate objective is to sculpt these powerful models into partners that are not only helpful but also fundamentally safe to interact with. The diagram on the right beautifully illustrates this. It's a continuous cycle. We provide feedback, which helps refine the large language model. This refinement leads to what we call aligned positive outcomes, outputs that are beneficial and in line with our expectations. This process is repeated, creating a constant loop of improvement. To achieve this, the entire concept of alignment is built upon three foundational pillars, being helpful, honest, and harmless. First, helpful. This means the AI must go beyond just processing words. It needs to accurately grasp the user's true goal and genuinely attempt to meet that need. It's about being a useful and effective tool. Second, honest. An aligned LLM must be a source of truth. It should provide factually correct information and crucially have the integrity to admit when it doesn't know something rather than fabricating an answer. This pillar is all about building trust. And third, harmless. This is the ethical safeguard. The model must be explicitly designed to steer clear of generating content that is dangerous, biased, unethical, or otherwise harmful. It's our commitment to ensuring AI contributes positively to the world. By focusing on these three pillars, we can guide the development of large language models that are not just powerful, but also principled and beneficial for everyone. For those of you who want to dive deeper, the source code of this tutorial and the project is accessible in our GitHub repository. You can have access to the link in the description of this video. Now that we understand what alignment is, let's explore what it gives us and what its limitations are. This slide tackles a crucial distinction. Alignment is a powerful path toward building trust in AI, but it's not a magic bullet for achieving full explainability. First, let's focus on the strong link between alignment and trustworthiness. Think about anyone or anything you trust in your daily life. Perhaps a skilled pilot or a seasoned doctor. You trust them because their actions are reliable, predictable, and consistently lead to positive outcomes. It's the exact same principle with LLMs. By meticulously aligning a model to be helpful, honest, and harmless, we ensure its behavior is consistent and acts in the user's best interest. As the Venn diagram illustrates, an aligned LLM and a trustworthy LLM are deeply interconnected concepts. Alignment is the how, trustworthiness is the result. However, the story changes when we compare alignment to explainability. Here, the link is much weaker, and this is a critical concept to grasp. Alignment is primarily concerned with the output, the what. It asks, is the model's final answer correct, safe, and useful? We are validating the quality and safety of the end product. Explainability, on the other hand, digs into the process, the why. It seeks to answer how exactly did the model navigate its billions of parameters to generate that specific output. This brings us to the black box dilemma, perfectly shown in the second diagram. We can have a model that is perfectly aligned. It gives us a validated, correct, and safe output every time. Yet the internal decision-making process that produced it can remain opaque. We can confirm what it concluded, but we can't always trace the precise path of why. So, the key takeaway is this. Alignment is our most effective tool for creating reliable, predictable, and safe AI that we can fundamentally trust. It solves the problem of behavior. But we should see it as distinct from the separate, ongoing scientific challenge of making these incredibly complex systems completely transparent. So, where is the field of alignment heading? This slide gives us a glimpse into the future, moving beyond the basics to explore the core philosophies and advanced techniques that are defining the next generation of AI. As the diagram illustrates, the path forward involves integrating three powerful and sophisticated approaches to build a more deeply and reliably aligned AI. Let's look at each of these pillars. First, we have AI-driven preference labeling. One of the biggest challenges in alignment is the sheer scale of human feedback required. It's incredibly time-consuming and costly. This technique is the solution. We are essentially training one AI model to understand human values and preferences so well that it can automate the process of labeling data for other models. Think of it as creating an AI supervisor that can apply human-like judgment at machine speed, breaking the bottleneck of manual work. Next, we have constitutional methods. This is a profound shift in philosophy. Instead of just telling an AI what not to do from the outside, we embed a set of core principles, a constitution, directly within its own operational logic. This gives the AI a framework for self-correction. It can review its own response, check it against principles like be helpful and harmless, and then revise it before it ever reaches the user. It's about building models with an internal moral compass. Finally, let's talk about advanced reasoning curricula. This is about teaching an AI how to think, not just what to know. Rather than just exposing a model to vast amounts of data, we create a structured training program, much like a school curriculum for a person. This curriculum is specifically designed to enhance the AI's ability to perform complex, multi-step reasoning and to follow a logical chain of thought. It's the difference between memorizing facts and developing true critical thinking skills. Ultimately, these three frontiers are converging. By automating feedback at scale, instilling principles for self-governance, and actively teaching complex reasoning, we are building the foundation for AI that is more capable, robust, and fundamentally aligned with human values. So, how do we actually implement alignment? Let's dive into the most common and effective method used today, RLHF, which stands for Reinforcement Learning from Human Feedback. As the diagram here illustrates, it's a dynamic, multi-stage process that creates a powerful feedback loop between human trainers and the AI model. The entire process begins with step 1, supervised fine-tuning or SFT. Think of this as the model's foundational education. We take a massive pre-trained model and give it its first taste of what we want it to be. We do this by training it on a high-quality human-crafted dataset of ideal conversations. This is like giving a student a textbook filled with perfect examples to learn from. This initial step teaches the model the basic style, tone, and safety protocols we expect. Step 2 is about building a judge. This is where we train the reward model. We take our model from the first step and have it generate several different responses to a variety of prompts. Then, human reviewers look at these responses and rank them from best to worst. This data, this collection of human preferences, is then used to train a completely separate model. The sole purpose of this reward model is to learn to predict which kinds of answers humans will prefer. It becomes an automated judge of quality. Finally, we reach step 3, reinforcement learning optimization. This is the most dynamic phase. The main LLM now operates in a live training environment. It generates a response, and our reward model, the AI judge we just built, immediately gives that response a score. This score acts as a reward signal in a reinforcement learning loop. Using a common algorithm like PPO, the model continuously adjusts its own internal strategy to try and maximize the rewards it gets from the judge. It's essentially a cycle of trial and error at a massive scale, where the model learns to consistently produce outputs that it knows will be scored highly by the human-calibrated reward model. So, in short, we first show it what good looks like, then we build a judge that understands our preferences, and finally, the model practices in front of that judge to perfect its behavior. This sophisticated three-step process is the engine behind today's most capable and aligned LLMs. Imagine you're a music producer trying to get the perfect vocal take. The old way is complicated. You first hire a panel of music critics to write a detailed scoring rubric for what good singing is. Then you use that complex rubric to coach the singer, take by take. It's slow, expensive, and often unstable. What if you could just sit with the singer, play them two different melodies, and say, "I prefer this one"? You just provide a simple preference. The singer learns directly from your choice, gradually steering their performance toward what you like. That, in a nutshell, is the breakthrough of direct preference optimization, or DPO. It's a powerful and elegant technique that scraps the complex machinery of traditional methods and teaches language models to be more helpful, safe, and aligned directly from simple human or AI feedback. Before DPO, the gold standard was reinforcement learning from human feedback, or RLHF. As the name suggests, it's a multi-stage process. First, you train a separate reward model. You show it thousands of pairs of model responses and ask humans which one they prefer. The reward model learns to predict which response will get a higher score. Second, you use that reward model as a judge in a complex reinforcement learning loop. Your language model generates text, the reward model scores it, and you use algorithms like PPO to nudge the language model's policy toward generating higher scoring text. This process works, but it's a beast to manage. It involves training two massive models. It's computationally expensive because you're constantly sampling from the policy, and it's notoriously unstable and sensitive to hyperparameters. DPO's authors asked a brilliant question. Can we skip the separate reward model and the RL loop entirely? Their key insight was this: your language model is secretly a reward model. Through a clever mathematical derivation, they showed that any optimal policy trained with RLHF has a direct fixed relationship with its underlying reward function. This means you can rephrase the entire optimization problem. Instead of training a reward model and then training a policy to match it, DPO defines the loss directly in terms of the policy itself. It collapses two complex stages into one simple, stable step. So, how does it do this? Let's look at the DPO loss function. It might look intimidating, but the idea is incredibly intuitive. For every training example, you have a prompt, a preferred response, Y sub W, and a rejected response, Y sub L. The DPO objective is to maximize the likelihood of the preferred responses over the rejected ones. Let's break it down. The core idea. At its heart, it looks at the log probabilities your model, pi theta, assigns to the winning and losing responses. The goal is to make the winner's probability go up and the loser's go down. The reference model, pi ref. You don't want the model to stray too far from its original stable knowledge base. The reference model, usually your initial supervised fine-tuned SFT model, acts as an anchor. DPO penalizes the policy for deviating too much from this reference, which prevents the model from forgetting its core capabilities or collapsing into repetitive outputs. The beta hyperparameter. This is your main tuning knob. It controls the strength of that anchor. A low beta keeps the model very close to the reference policy, leading to more conservative updates. A high beta allows the model to chase the preferences more aggressively, but risks instability. Think of it as the stretchiness of a leash. The sigmoid weight. This is the most elegant part. The entire term is wrapped in a logistic sigmoid function. This acts as a dynamic, intelligent weight. When the model already assigns a much higher probability to the winning response than the losing one, this weight is small. But when the model is wrong, when it thinks the losing response is better, the weight becomes large. This forces the model to focus its learning effort on the examples it's getting wrong, making training incredibly efficient and stable. In short, DPO increases the relative log probability of preferred responses, weighted by how incorrectly the model currently ranks them. The beauty of DPO is its simplicity. The practical pipeline is just 2 steps. Data collection. Start with a supervised fine-tuned SFT model. For a set of prompts, generate 2 responses. Have a human labeler or a more powerful AI. Choose the preferred one. This creates your preference dataset. If you're using a public dataset, this is already done for you. Fine-tuning. Optimize your SFT model using the DPO loss function. That's it. No separate reward model, no complex RL sampling loops. The paper even provides a PyTorch implementation that's just a handful of lines long. And if you don't have an SFT model to start with, the paper suggests a simple hack. Just fine-tune a base model on only the winning responses from your preference dataset to create a proxy SFT model before you begin DPO. So, does it work? The paper's experiments show a resounding yes. More efficient. On a controlled sentiment generation task, DPO achieved a better reward KL trade-off than PPO, even when PPO had access to the true ground truth reward function. This means for any given level of deviation from the original model, DPO gets you a higher reward. Higher quality. In summarization and single-turn dialogue, DPO consistently matched or outperformed strong RLHF baselines. For instance, in summarization, DPO achieved a 61% win rate against reference summaries, beating PPO's best performance of 57%. It was also the only computationally feasible method that significantly improved upon the chosen responses in the Anthropic dialogue dataset. More stable. The approach is far less sensitive to hyperparameters and sampling temperature than PPO, which can see its performance collapse under different settings. Direct Preference Optimization, or DPO, is a revolutionary, more direct approach, and today we're going to implement it from scratch to fine-tune the powerful LLama 3 model. In this video, we'll cover the entire pipeline. We have already explained the theory of DPO, so we'll dive into the code using cutting-edge libraries like Hugging Face's TRL and PEFT. We'll use techniques like LoRA for memory-efficient training and quantization to make this all possible on consumer-grade hardware. This is a complete end-to-end guide. By the end, you'll have a deep, practical understanding of how to take a powerful base model and align it with your own data and preferences. Let's get started. Before we jump into the code, let's quickly understand the 3 core technologies that make this project possible. First, Direct Preference Optimization, or DPO. Traditionally, to align a model with human preferences, a complex process called reinforcement learning with human feedback, or RLHF, was used. DPO is a newer, more elegant solution. It works with a simple but powerful type of data set, one that contains a prompt, a chosen or preferred response, and a rejected or less preferred response. The DPO loss function then directly optimizes the model to make the chosen responses more likely and the rejected responses less likely. It's more stable and often more effective than RLHF. Second, parameter-efficient fine-tuning, or PEFT, using a technique called LoRA. Fine-tuning a model with billions of parameters would require a massive amount of GPU memory because you need to store the gradients and optimizer states for every single weight. LoRA is a brilliant solution. we freeze the entire pre-trained model. All its billions of weights remain untouched. Then we inject tiny trainable matrices, called LoRA adapters, into the model's layers. We only train these small adapters, which represent a tiny fraction of the total parameters. This dramatically reduces the memory requirements, making fine-tuning possible on a single consumer GPU. Third, quantization. Even just loading a model like LLama 38B can take over 16 gigabytes of VRAM. To solve this, we use quantization. We load the model's weights using 8-bit integers instead of the standard 32-bit or 16-bit floating point numbers. This can cut the memory needed to load the model by 50 to 75%, making it feasible to run on more accessible hardware. By combining these three techniques, DPO for effective alignment, LoRA for memory-efficient training, and quantization for accessible model loading, we create a powerful and practical fine-tuning pipeline. So, you want to run this powerful AI model, but maybe your computer isn't quite up to the task? Don't worry at all. We can easily run this in the cloud using Google Colab Pro. The very first thing we need to do is give our project some serious power. Let's go up to the Runtime menu and click on Change Runtime Type. You'll see a pop-up window. The magic happens in the hardware accelerator. Instead of the standard GPU, if you have Colab Pro, you can select the powerful 800 GPU. This is a game changer for speed and will make running this model a breeze. Okay, with our 800 selected, let's get the software ready. We'll run our pip install commands to load all the essential Python libraries for this project. Next up, let's grab the code itself. We'll use a quick git clone command to download the entire project from GitHub. And just like that, we're ready to go. We'll move into the new folder and run the main script. And there it is. The model is running and generating its answer to our prompt. It's that simple to get started, even without your own powerful hardware. Let's start our code journey with dataprocessing.py. This script has one simple but crucial job: to prepare our dataset for the DPOTrainer. The DPOTrainer, which we'll see later, requires each example in our dataset to be a dictionary containing 3 specific keys: prompt, chosen, and rejected. Our format example function does exactly this. Let's walk through it. It takes a single example from our raw dataset and the tokenizer. First, it constructs the messages list that represents the start of the conversation. It checks if the example has a system prompt, and if so, adds it. Then it adds the user's question. Second, it uses a very handy function, tokenizer.applyChatTemplate. Every chat model has a specific format it was trained on, with special tokens to denote the start and end of turns. This function takes our list of messages and correctly formats it into a single string, prompt, complete with all the necessary special tokens. We set add generation prompt equals true to ensure it adds the token that signals to the model that it's the assistant's turn to speak. Third, it takes the chosen and rejected responses from the dataset and appends the tokenizer's end of sentence token to each one. This signals the end of a complete generation. Finally, it returns a dictionary with our 3 required keys, perfectly formatted for our DPOTrainer. This function will be applied to every single example in our dataset. Now let's move to the main event, training.py. This script orchestrates the entire fine-tuning process. We start by importing all the necessary libraries. We have Torch for our core deep learning framework, datasets and transformers from Hugging Face for loading our data and models, PEFT for our parameter-efficient fine-tuning, and TARL, which contains our DPOTrainer. Inside our train model function, the first step is to set up our tokenizer. We load it from the Hugging Face hub using autotokenizer.from_pretrained, pointing it to our base model. Then we configure it. We set the pad token to be the same as the EOS token, end of sentence token. This is a common practice for autoregressive models. We also set padding side equals left. This is a subtle but very important detail for causal language models. It ensures that when we batch multiple sequences of different lengths together, the padding is added to the left side so the final unpadded token of every sequence aligns on the right. This is crucial for efficient next token prediction. Finally, we explicitly define a chat template. While many models have this built in, setting it ourselves ensures maximum compatibility. This template uses a Jinja-like syntax to define exactly how a list of messages should be formatted into a string, using special tokens like imstart and imend to delineate turns. This guarantees our input is formatted perfectly. With our tokenizer ready, the next step is to load our data and our base model. First, we use load dataset from the datasets library to download our preference dataset directly from the Hugging Face hub. We're using the Intel Orca DPO pairs dataset, which is perfect for this task. Then, we use the .map method to apply our format example function to every single example in the dataset. This transforms our raw dataset into the prompt, chosen, rejected format that the DPOTrainer needs. Next, we load our base model, Unsloth Llama 3 8B. This is a special version of Llama 3 optimized for faster training. Let's look at the arguments to from pre-trained. Device Map Auto is a fantastic feature that will automatically distribute the model's layers across multiple GPUs if you have them, or load it onto a single GPU or the CPU. We also specify torch D-type torch bfloat 16. This enables mixed precision training, which uses a more efficient data type for calculations, speeding up training and reducing memory usage. Finally, and this is a critical step for combining quantization with LoRA, we call prepare model for KBit-A training. This function from the PEFT library does some important housekeeping under the hood, like correctly casting certain layers to ensure that gradients can flow properly through a quantized model during training. This makes our efficient fine-tuning possible. Okay, we have our massive Llama 3 model loaded in memory, but it's frozen. We're not going to train its original weights. Instead, we're going to use the LoRA technique. First, we define our LoRA config. This object holds all the settings for our LoRA adapters. Let's break down the key parameters. R is the rank of the LoRA matrices. This is the most important hyperparameter. A smaller R, like 8 or 16, means smaller adapter matrices and fewer trainable parameters, leading to faster training but potentially less expressive power. A larger R, like 64, gives the model more capacity to learn, but increases the memory requirements. LoRA alpha is a scaling factor that is often set to be the same as R, and LoRA dropout applies dropout regularization specifically to the LoRA layers to help prevent overfitting. Once we have our configuration object, we call the magic function getPEFT_model. This function takes our base model and the LoRA NAR-CFG, and it goes through the model's architecture, finds the target layers, usually the attention layers, and injects our small trainable LoRA adapter matrices next to them. It also handles freezing all the original weights. After this line, our model object is now a PEFT model, ready for efficient training. Now we're at the final setup step before training, configuring the DPO-Trainer. This is a fantastic high-level trainer class from the Hugging Face TRL, or Transformer Reinforcement Learning Library. It abstracts away all the complex math of the DPO loss function. First, we create a DPO config object. This holds all the training hyperparameters. Let's highlight a couple of key ones. Gradient accumulation steps is a crucial technique for training with small batch sizes. It allows us to compute gradients over several small batches and only update the model weights once, effectively simulating a much larger batch size without using more memory. Gradient checkpointing is another memory-saving trick that trades a little bit of extra computation time for a significant reduction in memory usage. We also set our learning rate, scheduler, and other standard training parameters here. Once our config object is ready, we instantiate the DPO-Trainer. We pass it our LoRA adapted model, our DPO-CFG, our processed dataset, and our tokenizer. One very cool feature of the DPO-Trainer is that we can set ref model equals none. In DPO, you need a reference copy of the original frozen model to calculate the loss. By setting this to none, the trainer is smart enough to automatically create and manage this reference copy for us, which simplifies our code a lot. After all that careful setup, the actual training process is beautifully simple, thanks to the Hugging Face Trainer API. We simply call trainer.train. This one line kicks off the entire fine-tuning process. The trainer will handle the training loop, moving data to the GPU, calculating the DPO loss, performing backpropagation, updating the LoRA weights with the optimizer, and adjusting the learning rate with the scheduler. It will also handle all the logging and progress bars for us. It's an incredibly powerful abstraction. Once the training is complete, we need to save our work. We call model.save pre-trained open parenthesis output directory close parenthesis. Because our model is a PEFT model, this command is smart. It knows not to save the entire multi-billion parameter LLM model. Instead, it only saves the tiny LoRA adapter weights that we actually trained. This is why our final output directory will be very small, maybe only a few megabytes instead of many gigabytes. We also save the tokenizer to the same directory. This is good practice as it bundles the exact tokenizer configuration with the trained adapters, making it easy to load everything together for inference later. Now that we've fine-tuned our model, let's see how to use it in Inference.pe. The load model for chat function handles getting our model ready for a conversation. First, we load our tokenizer from the base model and configure it with the exact same chat template and padding settings we used during training. This consistency is crucial. Next comes the model loading, which is a two-step process. First, we load the original massive frozen base model, just like we did before training. Second, we use PEFT model from pre-trained. This function takes the base model and the path to our saved adapter path directory, and it loads our small fine-tuned LoRA weights and merges them into the base model's architecture. We now have a single model object that has the full power of a Llama 3 combined with the specific alignment we taught it during DPO training. Finally, we switch the model into evaluation mode with model.eval. This turns off things like dropout. We also set use_cache equals true, which is an optimization that allows the model to reuse computations for past tokens, significantly speeding up the generation of long responses. With our model loaded, the chat function handles the process of generating a single response. First, just like in our data processing step, we use tokenizer apply chat template to format our system message and user message into a single, correctly formatted prompt string. Next, we use a very convenient high-level tool from the Transformers library, the pipeline. A pipeline abstracts away a lot of the manual tokenization and decoding steps. We create a text generation pipeline and give it our fine-tuned model and tokenizer. Finally, we call our generator with the prompt. We pass in several parameters to control the generation process. DoSample equals true tells the model to use sampling instead of just greedily picking the most likely next token, which makes the output more creative. Temperature controls the randomness. A higher value means more random, a lower value means more deterministic, and TopWP enables nucleus sampling, another advanced sampling technique. The pipeline handles the rest, and we simply return the generated text from the output. Finally, we have main.py, our project's entry point. This script serves as a command line interface, or CLI, that lets us control our entire application from the terminal. We use Python's built-in argparse library to do this. First, we create our parser. Then we add all the arguments we want to be able to control. The most important one is mode, which is a required choice between train and chat. This single argument will determine what our script does. We also add arguments for things like the base model name, the dataset, and the user message for chat mode. After parsing the arguments provided by the user on the command line, we have a simple if-else block that acts as a router. If the user ran the script with --mode train, we call our train model function from training.py, passing in the relevant arguments to start the fine-tuning process. If the user ran it with --mode chat, we call our load model for chat and chat functions from Inference, passing in the user's message to generate and print a response. This simple, clean structure allows us to manage both training and inference from a single, easy-to-use command. So let's take a moment to recap the powerful and modern fine-tuning pipeline we've just built. We've gone deep into direct preference optimization, learning how to use preference pairs to effectively align a language model. We've mastered an incredibly efficient workflow using quantization to load a massive model into memory and then using PEFT with LoRA to fine-tune it with minimal resources. We've structured this all into a complete application with clean, modular code for data processing, training, and inference. And finally, we've tied it all together with a flexible command line interface. You now have the knowledge and the code to fine-tune state-of-the-art language models on your own custom data. I highly encourage you to experiment. Find a different preference dataset on the Hugging Face Hub and try training with it. Tweak the LoRA rank R and see how it affects the model's performance. As a great next step, you could even take the inference script and wrap it in a Gradio UI to create a shareable web demo of your custom-tuned model. Thank you so much for joining me on this deep dive. If you learned something valuable today, please give the video a like and subscribe for more tutorials on cutting-edge AI techniques. Happy fine-tuning!